Hi everyone, I'm Yuhao Liang from Northwestern Polytechnical University. This is a description of our NPU-ASLP system submitted to the ISCSLP2022 Magichub Code-Swiching ASR challenge. First, we will introduce the background of Code-Swiching ASR, and then we will describe our data preparation methods and system architecture. Finally, we will introduce our experiments setting and the results. Code-switching has become a common language phenomenon which poses significant challenges to speech and language processing tasks, including automatic speech recognition. Language expert models model different languages by separated parameters in multilingual or cross-lingual settings, which can capture language-specific knowledge space effectively and mitigate overfitting caused by the poverty of code-switching data. To overcome the data sparsity problem, data augmentation might be a feasible solution. Some additional loss function and filter strategies are proposed for better use of synthetic data. In this challenge, we approach the Mandarin English code-switching ASR by exploration of both multilingual neural architectures and data augmentation methods. Specifically, we study the bi-encoder, language-aware encoder, and the mixture of expert architectures with two popular ASR toolkits, ESPNet and VNet. Various data augmentation methods, including speed perturbation, pitch shifting, audio codec augmentation, spectrum augmentation, as well as text-to-speech augmentation are applied on the training data. We further explore the effectiveness of language modeling, including both internal language model as well as long-context language model. Finally, ROVER is adopted for fusion of multiple hypotheses from various models. Our fusion system has achieved the lowest MER of 16.57% on the test set, leading our submission to the second place in this challenge. Our training data consists of two parts. One is the TAL-CS corpus, which is recorded from online one-to-one teacher-student English teaching. It contains roughly 587 hours. The other part is Magic Data RAMC, which contains 180 hours of conversational speech data recorded from native speakers of Mandarin Chinese or mobile phones. Data augmentation plays an important role in model training, especially in low resource or limited data scenario, and it can significantly increase data diversity and quality. Here we show the augmentation methods applied to the training data. We tried speed perturbation, pitch shifting, audio codec, and spectrum augmentation like most people do. Besides these signal perturbation approaches, we also build a text-to-speech system to synthesize extra training data using the transcripts of TLCS and the style of Magic Data RMC. In this part, we present our ASR approaches explored in this challenge. Our systems mainly contains of acoustic models, language models, and model fusion. As for acoustic models and language models, various architectures and training strategies are utilized. For acoustic models, we tried three variants of the encoder, including bi-encoder, language-aware encoder, and mixture of expert, which can lead to various outputs. Bi-encoder use two separated encoders to serve as Mandarin expert and the English expert for better capturing language-specific knowledge. It produces two different views of input code-switching audio and integrates by a gating network on frame level. Due to limited the data in this challenge, no monolingual English data is available, and outside data is not allowed to use. Hence, the Mandarin encoder is pre-trained on Magic Data RAMC, and the English encoder is pre-trained on TLCS, which is bilingual. Similar to biencoder, language-aware encoder also contains two parallel ASR blocks, as shown on the right of Figure 1. The main difference between LAE and biencoder is that LAE contains an ASR shared blocks followed by the ASR blocks. LAE can be explained as a variance of biencoder that shares the parameters of primary layers. Inspired by speech MOE, we further broaden the shared parts in the encoder so that only the last feedforward layer in each conformer blocks keeps separated. In our implementation of mixture of experts, the gating network is not utilized and the output of different experts are added directly. The detail of our MOE architecture are shown in Figure 2. As for language model, internal language model and long-context language model are explored besides standard transformer language model. Internal language model casts off higher level representation from the encoder and only use the current decoder state to produce a last state. Therefore, the SRC attention blocks is replaced by a feedforward neural network layer. Once the training of the entire AED model is done, we froze our other parameters and continue to train the feedforward block to minimize the perplexity on the training transcripts. Our target is conversational code-switching ASR, and leveraging context information has previously proven to be a significant factor in improving the performance of conversational ASR. We implement a simple way to augment code-switching text data for long-context language model training. Specifically, sentences in the same dialog are randomly concatenated by pairs in chronologically order. Thus, our text data for language model training is tripled in this way. The paired sentences are used to train a standard transformer language model, which covers long context from the transcripts. To achieve more effective TTS utilization, the ASR model is optimized with an additional consistency loss, which enforces posterior distribution similarity between paired real and synthetic speech. A callback labeler divergency between the posterior distribution of real data and the speech synthetic speech is used as consistency loss. We fuse the multiple outputs from the above ASR models by rover. The original rover is implemented by aligning multiple ASR results and votes with the same weights. We notice that there are many substitution errors on English words replaced by Mandarin characters which have similar pronunciation in code-switching ASR. Then we take unbalanced weights on English word and Mandarin characters during fusion. The weights are empirically selected on the dataset. All our experiments are conducted on ESPNet and VNet toolkits, and mixed error rate is measured on the official dev and test set of the challenge. We use a similar setting on ESPNet and VNet, only the frame length and frame shift is different. As for the acoustic model, the standard conformer based on Drone CDC is composed of 12-layer encoder and a 6-layer decoder. The number of heads for multi-head attention is 8 in all attention sublayers. For Mandarin, 4,340 characters are used as model units. For English, we use byte pair encoding to generate 1,000 subwords as modeling units. We set the CTC weight to 0.3, both in the training and decoding phase. The language model weight is set to 0.32 during decoding. The beam size is set to 20. We train 40 epochs for the conformer models with a learning rate of 0.0005. To verify the data augmentation methods, experiments are conducted to the standard conformer. In Table 1, the typical augmentation methods are examined on the conformers trained using VNet, while TTS augmentation is studied on the conformers trained on using ESPNet. We can see speed perturbation gets better performance compared with other signal perturbation approaches. Pitch shifting reduces accuracy when working with speed perturbation. Audio codec augmentation unfortunately leads to negative efforts, so we didn't merge it with other approaches. The use of synthetic data reduced 1.59% on the MER. Take benefit from the consistency loss, it brings 1.23% absolute MER reduction further. Encoder architecture are compared in Table 2. The baseline indicates the result of the official transformer-based baseline. From Table 2, we can see the obvious trend is that more shared parameters lead to better performance. This phenomenon is consistent in both the dev and test sets. We believe that this trend is mainly because the acoustic difference between the two datasets is not big enough and some exclusive parameters are redundant in biencoder and LE. We verify internal language model and long-context language model in Table 3. The standard transformer language model works better compared to internal language model and long-context language model in most cases. From the result of B3.1 and B4.1, internal language model and long-context language model do not show their advantages. But in our further analysis, they can produce different views of hypotheses from the acoustic model, and thus the final result will benefit from model fusion. The result of B3.2 shows that internal language model is harmful when it is used together with the transformer language model. We first examine the best single system before system fusion, and the results are reported in Table 4. Here, ESPNet is used for model training. With the help of speed perturbation and training using synthetic data with consistency loss, the LE and MOE system can achieve even lower MER on dev and test sets. Specifically, we set the Mandarin characters weight to 1 and adjust the English word weight from 1 to 5 accordingly. Results in Table 5 show that the weight of the English words is set to 4 times of that of the Mandarin characters. The best performance is achieved. Here, 16.87% is the MER our submission system obtained, and the gain from system fusion is significant. After the challenge, we take different language models into consideration and try another combination, and this post-challenge system gets a further MER reduction of 0.17% on the test set. This paper has described our Code-Swiching ASR system for the ISCSLP2022 Magichub Code-Swiching ASR challenge. In our approaches, ASR systems and their variants were particularly explored for acoustic model. Among them, MOE shows the best performance with the least language-specific parameters. As for language modeling, internal language model and long-context language model were studied besides the standard transformer language model. Eventually, the two language model can reduce MER by producing more candidates for the rover tool. The effectiveness of various data augmentation approaches, particularly TTS-based augmentation, were investigated as well. We find that additional consistency loss in model training can make better use of synthetic data and obtain further MER reduction. We obtain extra gain by using rover to fuse multiple hypotheses from various models. Compared with the official baseline system, our submission has obtained 11.17% and 9.63% absolute MER reduction on the dev and test sets, respectively. That brings me to the end of our system description. Thanks for listening.